All right, so let's talk about an application of some of the material that we've been learning, and in particular, I'd like to talk about communications and kind of focus on amplitude modulation. Okay, so we've learned a lot about filtering, maybe not so much about modulation, but these are kind of the two core ideas that really enable modern wireless communication systems, and of course also historical wireless communications. So early AM radio systems back in the early 1900s. Okay, so to kind of just define these terms, modulation is just the idea of multiplying a kind of, you can think of a low frequency or band limited signal by a high frequency carrier. Okay, and this allows us to shift the spectrum of a signal up into a range that makes it easier to transmit using electromagnetic waves, using smaller antennas, and it also allows us to put multiple signals up at high frequencies. It's kind of separated in frequency itself, and then demodulate them and extract just a single signal or a single channel at a receiver. Okay, so the second idea, of course, is filtering, and that just allows us to extract components or frequency bands from a large spectrum that contain the signal that we're interested in, the signal that was transmitted somewhere that we'd like to tune into. Okay, so on the bottom there's a diagram of a kind of standard AM radio setup. And there's a bunch of different things, but the first thing, starting all the way on the left, is AFT. And so think of that as the audio signal, right? Could be data, right? So if it's audio or if it's just a voice signal, we've seen that a lot before. If it's data, you can just think of it as being kind of a high value and a low value indicating a 0 or a 1. And of course, I mean digital data, so zeros or ones. So that gets multiplied by a cosine. Cosine's at some higher frequency, particular at frequency of f sub c, which stands for carrier frequency. And so this is the modulation step, and the reason it's called modulation is because we're now modulating this high frequency cosine by a signal that's carrying the audio or data that we're interested in. Okay. So that gets transmit, and that goes over the air, and then at the receive side, there's a couple of things that happen. The first thing is it gets multiplied. So in practice, of course, there's an antenna here, and there might be some filtering immediately after the antenna, but we're just going to ignore that for now. So what do we see at the other end? It's not just AFT. It's there's a bunch of other signals, right, from other, you can think of other radio stations that are also included in this time domain signal, right? But still, we're just going to take that received signal, right, that consists of AFT and a bunch of other signals, and we're going to multiply it by, again, by cosine 2 pi FCT, and this is referred to as demodulation. Okay, and the idea here is you're taking away that carrier. So we'll see on the next page when we go through this by multiplying by a cosine at the same carrier frequency, and then we bring the original signal AFT back down close to center frequency of 0. So then the next thing that happens is filtering. Okay, so we're still in the analog domain, but filtering is now, the goal is, even though we've multiplied by this cosine 2 pi FCT to demodulate the signal, there's still a lot of other signals around. So we're going to filter, and then we'll have finally have some signal on the other end that hopefully is something like AFT. Right? And as we go through this, we'll look at what happens when we put a sampling block here after this final filter. So the first thing we should think about is the spectrum of AFT. And remember, that could just be speech, it could be music, or it could be some sort of data. But the point is, and we've seen this before, that we can write any continuous time signal as a sum of sinusoids, right? And we can approximate it by a finite sum of sinusoids of just n sinusoids. So that's kind of what I'm drawing, or what's shown in this picture below. is we have some signal A of t, and it has a spectrum, but the spectrum is what's called band limited, meaning that it has some maximum frequency component and some minimum frequency component. And that maximum and minimum frequency component are just denoted by f sub m and minus f sub m. Okay, so this gets multiplied. Think of this spectrum getting multiplied by a cosine. Right? Cosine at frequency of fc, the carrier frequency. So that's just written down here. And so what does this do to the spectrum? Well, we went through this briefly before, but if we kind of expand everything out using Euler's identity, or if we just remember the kind of, there's a identity for multiplying two cosines together. You get a cosine at the sum and the difference of the frequencies. Okay, so what this does to the spectrum is it shifts that original spectrum that used to be centered around 0, right? This thing looked the same, but it used to be centered around 0. It really multiplies it by 1/2, so the amplitude gets smaller by 1/2. But it shifts it up to some high frequency, fc. Okay? And so now there's a copy also at minus fc. And if we go up to these equations here, so I've just multiplied this first term, right? And that term is the audio signal, just the Fourier series expansion you can think of the audio signal. And then the second term is Euler's identity applied to cosine, or Euler's inverse identity. Multiplying all these terms out, what you see is the components in that original spectrum that was centered around 0 then gets shifted up to plus fc or minus fc, right? And that's exactly what's drawn in the picture here. So then this signal gets transmitted over the air, right? So let's call this signal x of t, and this gets sent to, ends up being a voltage on a wire, and that goes to an antenna, and that creates an electromagnetic wave. And that electromagnetic wave then travels over the air and then is received at some other location. We'll just call that signal r of t. So you don't just receive the single station you're interested in. Of course, there's a number of other stations. So you receive all of these other stations. Okay, but if you'll notice, the stations hopefully don't overlap. In particular in AM radio, hopefully they don't overlap and they're not at the same, and think of the same, they don't occupy the same spectrum as the signal you're interested in. So we have these other stations, and we have noise and interference, and all this stuff gets picked up at the receive antenna. So the question is, how do we get back to A of t, right? How do we get back received signal again by a cosine 2 pi fct? Remember, this is what was on the block diagram, and that's just called demodulation. So what happens when we do that? Well, we'll call that signal y of t. Okay, so here r of t is the signal that arrives at the antenna. Then it gets multiplied by cosine 2 pi fct. And somewhere in there is A of t times cosine 2 pi fct, right? That's what got transmitted. And of course, we're ignoring kind of propagation effects. When these things propagate, of course, the amplitude would also get smaller. So this leading term would be some fraction, of course, of what was sent originally. But now we have two cosines, right? Here's the one that we multiplied with in the modulation step. Here's the one that we multiply with in the demodulation step. And of course, there's all these other channels. We're kind of going to ignore for now what happens to them, but just understand in pictures when we look at the spectrum. So cosine times cosine at the same frequency, you get a sum and difference formula for the frequency of the resulting cosine. And what that equals to, you get, since we multiplied by fc when we transmit and multiplied by fc when we receive, then we get a DC term. It's the difference between fc and fc is 0. So that's a DC term. So you get this 1/2 A of t plus 1/2 A of t cosine 4 pi fct plus a bunch of other stations, right? And so that, what that does is that brings down the spectrum of the station we're interested in, this term, that gets centered around 0 again. Right? But then there's also another copy and that's maybe way up at some high frequency here. Okay? So that's also the station we're interested in, but we're not going to use that copy. We're actually going to filter that away. Okay? And then there's of course all the other stations, all the things that we don't want that we'd like to just remove from the signal. Okay, so how do we do this? Well, the first thing we're going to do is pass it through a low-pass analog filter. And this is a good thing to do because we're going to sample this, right? We're going to look at this digitally. It's not necessarily how receivers used to work, but they more or less all modern radios that you could probably even buy now are all digital. So how does this work? Well, before we sample, we need to pass through an analog filter. And the reason we need to do that is we need to avoid aliasing, right? Remember, if we don't pass through this analog filter, there'd be all this stuff out here, right? And if all that stuff is at a frequency higher than 1/2 the sampling frequency, we're going to have aliasing. So this is called an anti-aliasing filter. It's a low-pass filter. Another name for the filter in this spot is called anti-aliasing. And the reason we have this is to avoid aliasing. So of course, this antenna has picked up very high frequency stuff, right? Especially after demodulation, after multiplying with this cosine wave. Okay, so this filtering step is going to remove, it's definitely going to remove this term. Okay? That's the term that's at twice the carrier frequency. It's going to let this term pass, 1/2 A of t, and it's going to get rid of maybe a few of the other stations, but not necessarily all of them, right? If we look at this picture, we're still letting some of these other stations go through, right? The ones that are very close. And you might ask, well, why wouldn't you just design an analog filter that's very strict, that only allows the station you're interested in to pass? And old receivers, old communication receivers definitely operated this way, and this is exactly what they did. But these filters are actually, if you're going to mass produce something, it's expensive to have a lot of capacitors and inductors. Right? If you're making millions of a product, it can get expensive, and so you want to make cheap filters. You want to do it using as few inductors and capacitors as possible. Right? So then what you'd end up designing, say, well, I can design this filter, kind of this loose filter drawn above, using way fewer capacitors and inductors than I can with this filter. Then I need to design this filter. And then after I sample the signal, we can just filter it in digital. Okay? And so that's exactly what the principle is, what we're going to do. So kind of the last step is we're going to sample with an A to D at a frequency Fs. Okay? And we want Fs to be greater than or equal to twice the cutoff frequency of the low-pass filter that we had drawn on the other page. And that just avoids aliasing. Okay? So then the spectrum of this discrete time sequence, x of n, right, it should look about the same, and now we're plotting f hat, the digital frequency from a range of -1/2 to 1/2 units of cycles per sample. And so now this is our digital sequence after we've sampled it. Okay, so the fourth and final step is to apply a digital filter, and maybe that's a FIR filter. And we're going to talk about how we would design this filter. So this filter, right, is kind of, you think of this as an ideal low-pass filter, meaning it only allows low-frequency components to pass, and they pass through perfectly, meaning this has amplitude 1, and then everywhere else it has amplitude 0. And if we do that, we're just left with the audio of the radio station. Right? And then we could play that back, for example, in MATLAB using Sound SC, and we'd be done.